come finally to the definition of an integral. But first there is some notation that we'll use for expressing sums. Here I consider the sum of n terms, a1, a2, a3, and so on up to an. The left-hand side is a shorthand for this sum, which makes use of the Greek capital letter sigma, which is the equivalent of the Latin letter s, which stands for sum. We read this as the sum of ai as I goes from 1 to n. This means we take all terms ai with I in the range from 1 to n, that is, every integer in the range from 1 to n, and add up these terms. For example, here is the sum of the squares of the first 10 positive integers. Its value is 385. In my previous examples, the letter I served as what we call the index of summation. Here, I'm using j instead of I. It doesn't really matter what letter we use. This sum asks us to take the expression f of j minus 1 divided by 2j, and then to replace j by all the integers in the range from 1 to n. Then add up these numbers. The right-hand side shows the long way to write this sum. Here's another numerical example. Take the expression 1 plus k over k squared. Replace k by all the integers in the range from 2 to 5 inclusive. This gives 4 terms, and we add them up. What's the point of this notation for sums? For one thing, it's probably shorter to write the sum using summation notation rather than writing out the terms explicitly. More than that, the summation notation explains what the pattern is in the terms. In this last example, if I hadn't told you that these fractions were all of the same basic form, 1 plus k over k squared, just for different values of k, you might well be at a loss to see the pattern in what I was writing. And there's no point at which this notation for sums is absolutely required for what we're doing, which is to introduce integrals. In place of the summation notation, you can pretty much get by with writing out the terms with ... like in the first 3 lines here. However, the book uses this notation for a good reason. And as you'll see, it's designed to make our life easier. It also helps us to understand our notation for integrals when we get there. It's a notation we've already mentioned before in previous videos. Now here's a fairly generic picture of a graph of some function f defined on an interval AB. I've chosen this function to be positive just to help with the interpretation of what we're doing. This curve forms the upper boundary of a plane region. I would like to know what the colored area is, by which I mean the area between the curve and the x-axis, just between x equals a and x equals b. This is the question you would ask yourself if you had an irregularly shaped object and you wanted to know how much paint would be required to paint it. In real life, your object might not have 3 straight edges like this one does, but the problem we are asking is so basic that it answers the general case for areas of general plane regions. It also answers questions about volumes, masses, lengths of curves, costs, amount of traffic, center of mass, population, on and on, you name it. This is just so many applications for integrals, as we'll see in due time. And the technique we're describing is attributed to the 19th century mathematician Bernard Riemann. And yes, he really did live only 39 years, but he is also considered to be one of the truly great mathematicians of history. Here you'll hear his name a lot in this video, but first some general remarks. We can say roughly that there are 2 main branches of calculus, differential and integral calculus. The first part, which we've highlighted up until now, has been differential calculus. We have been discussing derivatives, which are rates of change. And very close to the start, we focused on a particular graphical interpretation of derivative, which is slope of the tangent line, the graph. But by now you should have realized that The graphical interpretation of derivative is just one of a huge number of interpretations. And in a similar way, integrals are about much more than areas of shapes like the one you're looking at here. There's just one graphical interpretation that serves as a quick start to defining the integral. And later we'll see that integrals are not so limited or two-dimensional as this picture implies. But you should remember that to understand derivatives as slopes of tangent lines, we started with an approximation, which was slopes of secant lines. And from there we took a limit to get the actual value of the derivative. In order to understand the problem of area, we also start with a sequence of approximations. Then we take the limit to get the final answer for the area. This limit actually defines the integral of our function over the interval AB. So how do we compute this approximation to area? Our approximation is based on areas that we know, which basically means rectangles. The area of a rectangle is just length times width. So we divide our region into vertical strips, which are almost rectangular. In my example, I will divide the interval AB into 6 subintervals. All my subintervals will have the same width, delta x, which therefore equals the width of the entire interval, b minus a, divided by 6. I'm using 6 subintervals just for the purpose of illustration only. In practice, we'll want n subintervals, and the resulting approximation for area under the curve will be better if n is chosen as large as possible. The points at which my interval AB has been subdivided are called x0, x1, x2 up to x6. Of course, x0 is just the left endpoint a. Then x1 is a plus delta x, and to get x2 we add another delta x, add another delta x to get x3, and so on until you get to x6, which is a plus 6 delta x, which is b, and then you solve for delta x and you get the formula that I have. The vertical strips are approximately rectangles, all of width delta x. It's just the heights that are different. The heights are found by evaluating the function f, which you can evaluate at our xi's and approximate these strips as rectangles. There's just some ambiguity, however. What's the best choice of rectangles to approximate our vertical strips? And one standard choice is called the right Riemann sum. Here we measure the height of the curve at the right endpoint of each subinterval. So we take each height multiplied by the base delta x to get the areas of the 6 rectangles shown. Add up these rectangular areas to get our approximate value for the area under the curve. Look carefully at how the sum comes out and how we have rewritten it using summation notation. Now a different choice would be the rectangles shown where the heights are the function values at the left endpoints of the 6 subintervals. Again, take the function values for the heights of the rectangles, multiply by the base, which is again delta x, to get the area of each rectangle. Add these up to get the total area of the 6 rectangles. This gives a different approximation of the area called the left Riemann sum, for obvious reasons. And you'll notice that in both of these sums I have described the base delta x is a common factor. It can be taken outside the sum. From a practical point of view, both the left and right Riemann sums arise from starting with a table of values for the function f, evaluated at equally spaced points, add up n entries from our table of values, multiply that by delta x. However, in my notation, I'm choosing not to factor out this delta x outside the sum for reasons that maybe will become clear later. Now here's a variation which often gives a better estimate for the area. Evaluate the function at the midpoint of each of these subintervals. The midpoint of each subinterval is the average of the two endpoints of the subinterval. Evaluate the function at each of these midpoints. These values times the base, again delta x, will give the area of each of these rectangles. Add up the 6 rectangular areas, you get the approximation to the area under the curve, which this is called the midpoint Riemann sum. Look carefully at this picture and see if your intuition agrees that, as I've suggested, this estimate for the area under the curve is usually more accurate, you would expect, than the left or right Riemann sum. Here is yet another kind of estimate for the area. We take the maximum of f on each subinterval. And we use these as the heights of our rectangles. Again, multiply these heights by the base delta x, add them up to get the upper Riemann sum. This is probably not as close as the other estimates we've mentioned. It's in general an overestimate for the area under the curve. This might be useful, however, if what you really want is not the most accurate estimate for the area. What you really want is perhaps an overestimate, so you can be sure that the area is not more than a certain amount. Now, in some applications, it might be hard to compute the upper sum, since it requires solving a maximization problem on each subinterval. Notice my notation. I'm writing xi star for the point in the ith subinterval, the point on that subinterval where f is maximized. There's probably a better name for this point, but xi star will do for us. Of course, if your function is increasing, then the upper Riemann sum is nothing different from the right Riemann sum. And for a decreasing function, the upper Riemann sum is the same thing as the left Riemann sum. Please pause the video, rewind if necessary, to convince yourself that this is true, what I'm saying, for rather obvious graphical reasons. Don't think too long about it. Alternatively, we might want to underestimate the area under the curve. We can do that by taking heights of rectangles to be the minimum values of f on each subinterval, as shown. Multiply these values by the base, again delta x, add them up, and you get the lower Riemann sum. If you compute the upper and lower Riemann sums, then you don't know the exact area, but at least you know that the area is for sure between these two values, the upper and lower Riemann sums. Again, for obvious reasons, if you think about the graph, if a function is increasing, then the left Riemann sum is the lower sum. If a function is decreasing, the right Riemann sum is the lower sum. Please pause and think about this using a graph before we go on. We've looked at some examples of Riemann sums with 6 subdivisions. Let's go on to n subdivisions, where n is probably much larger than 6. As you would expect, choosing a larger value of n leads to a closer approximation to the area under the curve, since it allows the rectangles to stay closer to the nuanced shape of the curve. We'll fix the function f, also the interval a, b, but we allow n to be arbitrary. Ultimately, we want to see what happens when n gets larger. Here we'll consider a Riemann sum with n subintervals. And as before, we divide the entire interval ab into n subintervals of equal width, which is delta x. That's equal to the entire width, b minus a, divided by n. And I will name the points where the interval gets divided up. Those points will be x0, x1, x2, all the way up to xn. The ith subinterval is between 2 consecutive points of this subdivision. That's from xi minus 1 to xi. Explicitly, The points xi are given by this formula. Take the left endpoint, a, and add I times delta x, and you'll get x sub I. Now, my picture looks like a right Riemann sum, but I want to consider a much more general approach, which includes all types of Riemann sums that so far we've considered. All these Riemann sums look like this. It's a sum of n terms, which are areas of rectangles, and each term is the base, delta x, times the height, which is some value of the function, where the function has been evaluated at some point xi star inside the ith subinterval. And the different methods are just different choices of which point you choose. For example, if your xi star is the right endpoint of the subinterval, then you just get the right Riemann sum. If xi star is chosen as the left endpoint of that subinterval, then you'll get the left Riemann sum. If xi star is the midpoint of the ith subinterval, you'll get the midpoint Riemann sum. If xi star is the point in the ith subinterval where f is maximized, this will give you the upper Riemann sum. If xi star is the point in the ith subinterval where f is minimized, this will give the lower Riemann sum. So once again, all our Riemann sums can be described using this general description. In each case, we sample the function on each subinterval, use that point, evaluate the function there, and you'll get the height of the corresponding rectangle. Different choices of points, xi star, will result in different Riemann sums with varying degrees of usefulness or goodness of the approximation to the area under the curve. Finally, we define the Riemann integral of f from a to b. Using this notation, it is defined as the limit of the Riemann sum as n goes to infinity, n being the number of subintervals. So now look closely at the notation. Notice that in our limit, the capital Greek letter sigma becomes replaced by the stylized letter s in our integral. The function value f of xi star is replaced simply by f of x. And the difference, delta x, is replaced by the differential dx. And the strong analogy in the notation between the sum and the integral should be a huge help in setting up your work, your sums and your integrals, setting them up correctly. After hinting at this connection for so long, it's good to finally see the integral notation in use here. But there still remains the mystery of how this is connected to antiderivatives. We're not there yet, so hold your horses. It won't be too long yet. Now, how do we actually know that this limit exists? Well, it might not, depending on the function f, but if f is continuous, then we know for sure that the limit will exist. In fact, even for most discontinuous functions that we've considered in our course, the limit will still exist. So if the limit exists, if this limit exists, then we say that f is Riemann integrable, and the limit defines the value of the integral. There are some examples where f is not integrable, meaning the limit does not exist, but don't worry about them too much right now. Suffice it to say that it's pretty easy for a function to be integrable, much easier than to be differentiable. In fact, being differentiable is stronger than being continuous, which in turn is stronger than being integrable. So Very few functions are differentiable, more are continuous, and more than that, much more are integrable. Now, I also need to say something here about the choice of the xi stars, because that will change the Riemann sum. But at least in the case of continuous functions, and actually for most of the functions we'll consider, it doesn't really matter which xi stars you choose. It doesn't change the limit. Meaning, for example, the limit of the right Riemann sum, if the limit of the right Riemann sum exists, as n goes to infinity, then the limit of the left Riemann sum also exists and equals the same value. Also, the limit of the midpoint Riemann sum, also the limit of the upper sum, also the limit of the lower sum. They all exist and give the same value. Different choices of xi star can affect the accuracy of your estimates for a particular n, or it'll tell you, different xi stars will mean you have to make n bigger to get within a certain accuracy of the true value of the integral. That can be important for practical reasons if you're trying to approximate, if you're trying to estimate the integral, but it cannot change the value of the limit. I will also mention that there are other definitions of integral other than Riemann integral. There's like a Lebesgue integral in particular, an important one. You'd have to learn about that in an analysis course, not here. And to see how these other integrals improve over the Riemann integral, you'd have to look at functions which are very different from the ones we're looking at in our course. So for us, you don't need to consider that. For us, the Riemann integral is the integral. The Riemann integral really does answer our original motivating question. It answers, what is the area under the curve? I was very careful in the wording of the question. When I ask what's the area, I'm not just asking you how do you compute the area, but what is it? How do you define it? Because for us, the shaded region is how you define the area. You might think that you can define the area without having to do an integral, but it's really only for very simple shapes like rectangles or triangles that you can convince yourself of the validity of some formula that you've learned to trust. And for general shapes, like I've shown you here, you really can't talk about what area is, even what it is, much less compute it, without first defining an integral. Now, I do need to caution you that the straightforward interpretation of the Riemann integral as area is not valid if b is less than a, or if the function is negative in some parts of the domain. The formula shown here for the integral is correct, but if the function is negative, then that will make terms in the sum negative, so the integral can end up being negative. For that reason, it cannot be area, because area cannot be negative. Integrals can be negative, but area cannot be negative. Likewise, if one integrates from right to left, the delta x's become negative, which reverses the sign of the integral. And again, you can't talk about a negative value for area, but you can for integral. All these things we'll talk about soon enough. Now let me come back to this one other point about restricting the subintervals to have the same width, delta x, the way I restricted the integral for the Riemann sum. There's some reasons why this restriction might not be the best in practice. For example, look at this curve. You're trying to find the area under the curve, and if I happen to choose a right Riemann sum with n equals 6 subdivisions, this does not estimate the area under the curve very well at all, due to this one tall blip, which the rectangles don't capture very well. And to fix that, you can take 6 subintervals of varying width, and the narrower subintervals, where the xi's are closer together, can be placed in the region where the curve is steeper. And then you get a right Riemann sum that comes much closer to the actual area under the curve. This is still part of the full description of a Riemann sum. It's more general than the one I gave. So my description of Riemann sums was unnecessarily restrictive in my requirement that all the subdivisions have the same width delta x. So another approach is to divide the interval AB into n subintervals of arbitrary width. But then you have to be careful how you take the limit. So you can't just let n go to infinity. If the number of subintervals goes to infinity, but they're varying width, some of the subintervals might shrink to 0 and others not. If some of the subintervals stay large, then there are going to be large regions where the rectangles never get close enough to the curve. So the proper limit process here requires that all the subintervals shrink to 0. In other words, one requires that the maximum size of the subintervals shrinks to 0 to define the Riemann sum.